We'll be looking at question 17, June 2024 paper. In this question, you've got crystal violet is a purple dye. In the presence of an alkali, the crystal violet or CV reacts to form a colorless product. The student uses a colorimeter to investigate the rate of reaction between CV and sodium hydroxide. The student mixes this volume concentration of CV with this volume concentration of NaOH. A large excess of NaOH is used so that the reaction is effectively zero order with respect to hydroxide ions. So that's going to be a useful bit of information for later on. The student places a sample of the reaction mixture in a colorimeter and measures the absorbance over time. The student uses the absorbance readings to calculate the concentration of CV and plots a graph of concentration against time. We have seen concentration time graphs many times previously. This is what you've got here. Notice this concentration, this initial concentration is actually half of this because you've got two solutions mixed together with the same volume, which in essence halves the initial concentration, if you're wondering. Now, you've got the concentration time graph. Before we answer the main question, it's asking you using collision theory, which we learned in year 1. Using collision theory, explain why the gradient decreases over time. Why does the gradient? So initially, the gradient's this, but over time, it gets less and less over time. We could draw longer lines there to get a more accurate gradient. And there's 2 points to this. You see, as the concentration decreases, let's write this down. As the concentration decreases, we're using collision theory from year 1. As the concentration decreases, what happens is that the collisions become less frequent. As the concentration decreases, the collisions become less frequent. I'm just going to go off at a tangent here. You know what? When we, for example, if it was temperature, if we were decreasing temperature would actually result in collisions becoming less successful. So successful and frequent collisions are linked with concentration, and successful collisions are linked with temperature. Bit of a year 1 idea there. Anyway, moving on to the question. Use the graph to determine the... Actually, let me just stop there for a moment. Ladies and gentlemen, with these types of questions, when you've got just a couple of lines and you see all this blank space, naturally, our psychology can make us sort of almost shut down, thinking this question is too hard. No, it's not. You need to break it down, read the question carefully, and extract what they are asking you. They are telling you to use the graph to determine the order of reaction with respect to CV, the rate of reaction at 3 minutes, and the rate constant. So, first of all, to work out the order of reaction with respect to CV, what we're going to do, let's look at the graph. Whenever you see a concentration time graph and you're required to determine the order of reaction, the first thing usually good to do is determine if the half-life is constant. So if we use the initial concentration, and If we halve that to 0.7, which gives you this. So let's that line is slightly off. Let me just start there. Here, you can read that off. And you've got the initial concentration from there to there. You can see that the half-life, the time taken for the concentration to halve, is 2.5 minutes. Let's take another concentration time graph. We could take it anywhere, really. Let's do from 1.0 to and half of 1.0 times 10 to the minus 7 is 0.5. So let's take it from there. And here, 3.75 minus 1.25, that is also actually exactly on 2.5 minutes. So what we've got, the half-lives are constant half-lives as shown on the graph correspond to first order with respect to CV. So we've done the first point. We've determined the order of reaction. Let's now work out the rate of the reaction at 3 minutes. So let's get a different color pen. Let's use red. 3 minutes is over here. So let me just highlight that. And we need to draw a tangent. We need to draw a straight line where the straight line is resting on the graph at 3 minutes. So I did this with a ruler on the paper. And so I saw it cut off around here. There you go. Let's now work out the rate of reaction, which will be concentration divided by time. What we've got here, if we read off here, I've got here 1.12 divided by, actually times 10 to the minus 7 divided by 6.5 minutes. What does that give us? (1.72) times 10 to the minus 8 moles per decimeter cubed per minute. Oops, per minute. Be careful of your units, and this is the calculation that we would use to determine that. Okay, you'd obviously write this down where the lines are. You'd write that down here. So we've determined the rate of reaction. We said it's 1.72 times 10 to the minus 8. We've determined the rate of reaction at 3 minutes. And the next bit is the rate constant. to work out the rate constant, we are going to substitute values. So let's use a nice green color, my favorite color. Let's work out the K constant. Now, we know that the rate equation is equal to K CV, which is first order. And remember, hydroxide ions were zero order, and anything to the power of 0 is actually equal to 1. So we can cancel that out. We've got that. Now, let's use the data from 3 minutes. So we'd write down 1.72 times 10 to the minus 8. Let's divide that by CV concentration at 3 minutes. CV concentration at 3 minutes. I've got here 0. I believe 61. 0.61 times 10 to the minus 7. 0.61 times 10 to the minus 7. Let's see what that gives us. Actually, I'm going to use 1.72 minus 7. Let's divide that by 0.61 times 10 to the minus 7. Oops, I've got a wrong power here. 1.72 times 10 to the minus 8, not 7, divided by 0.61 times 10 to the minus 7. Close the bracket. Yeah, that gives you 0.281. What would the units be? The units would be rate, which is moles per decimeter cubed per minute, divided by moles per decimeter cubed. Ladies and gentlemen, we are used to seeing a rate in concentration per second, but in this graph, we're seeing the time as minutes, so we're using minutes. So these cancel out, and you're left with minute to the minus 1, min to the minus 1. That is your rate constant. Now, this is something that you don't get asked often in past exam paper questions, but it does creep up every now and then. There's an alternative way to work out rate constant using half-lives. How do you do that? You do that in the following way. Let's use pink. You see, there's an expression, the K constant is equal to the natural log of 2 divided by the half-life. Now, we know the half-life, we calculated that as 2.5 minutes. So if you, on your calculator, do natural log of 2 divided by 2.5, you'll notice you'll get K is equal to 0.277, which is very close to this as well. And the units as per minute. So this is an alternative way to work out the K constant. And I believe we have worked out everything and we've got our answers. So about half of the marks, 4 marks are from your writing, and about 2-3 marks are from your graph work. This is an essay style question, so they look at overall, holistically, how you've answered this question. Write it in clear sentences and explain clearly what you've done, like we've done here. Okay? And that is that. See you later on. Thank you.